All right, fire away, Akrapan.
Sure. Okay, I would like to ask about finishing, right? There are many type finishing. It's depending on the purpose of using, right? Like a
Yes.
tie or like a covering, particle melamine or other thing. So I'm not sure which one is appropriate for the hollow core, or it's not matter on which type of floor we use.
So you are asking the question about the floor, right?
Yes, for
So
the
let's
finishing.
go to the floor, but I think I'll come back on the floor again. But I
Sure.
think we have had quite a good understanding about the floor. You just pick the floor on this side, right? So that becomes your span length. Then the load you put on the floor will be your information that is called the superimposed load. Now you can pick the floor. Now you asked me about the type of the appropriate finishing. That's a very good question. But the thing is, I think it doesn't really matter because hollow core is there just to support the floor system. Actually, the hollow core itself is a floor system. So it's there to support the live load and whatever finishing you put on. So you are actually free to use any finishing. Unfortunately, I have to say this, but it's true. In real life, unless you are the owner of this building, you don't get to choose finishing, you know, because that's the architect's job. They have knowledge in abundance, you know, so they really know what kind of floor that you should use. And it depends most of the time on the owner's need, what kind of floor you want, right? Because some would say, you know, I like marble. I want to feel like Julius Caesar. So they're going to have marble, but marble requires additional system so that it can be laid on the floor. So for the marble, the date load is about 200 kilograms per square meter. It's pretty heavy. Granite, for example, it's 100. And see, my finishing on in this room where I'm sitting is the tile that is supposed to give me a feeling like I'm walking on the beach. That's the idea of the architect, you know. I asked him why it's a little rough, you know, when you walk on it. So it kind of gives you a feeling like you're walking on the sand. And it doesn't really matter. Say it doesn't concern the type of floor that you choose, no.
Okay, I see.
Anything more before we begin wrapping up the work that you have to do on your truss?
Just this one only, because I try to find the type or which one will be appropriate for the school or my occupancy. Yeah.
No, this is a very important thing because I want you to feel familiar with what you need to do. Okay, you don't go around and say, hey, what is this? You don't design without knowing anything. And mark my words, most of the time, the most important step is just the load. Okay, if you miss the load that you're going to put on the structure, that can be very fatal. In other words, or you know, when you look at the structure, say if you miss the analysis, if you do something wrong, if your system is stable, you know, if you do the job so bad and you have the system that is unstable, that's out of the question. You know, if your structure is going to collapse. But say if you have a sound system and you perform improper analysis, say you're going to be off 10-20%, that's it. But say if you miss the load, for example, when you calculate this beam, you know, and you miss that this beam has to carry the floor from the left and then from the right, you account for only floor from the left. So you're going to miss the load by 50%. So chances are your structure will not survive. And you will see even before it is being put to use, because the deflection is going to be so large and the size of your beam is going to be so small. You know, when you look at the structure under construction, you feel, is it going to be okay? Okay. So if there is any case, let us go back to the rules. Okay. Let me repeat again that you are going to design just the truss. Okay. You don't have to design the purlin. However, the purlin will be put in this direction. See the green ones. Generally in the drawings, you will see something like this. they're not going to show the entire purlin. So they would just cut the section like this, you know, that sort of thing. And then they will show the purlin. Because once you cut the roof out, you see the purlin, right? That's how you're going to see it. And then they say, okay, this is purlin with the member 4.5. Maybe I'm guessing purlins C100 by 50 by 20 by 3.2 at every 1.5 meters, for example. Okay, that's what you're going to see. Now, you know that from this, I am going to say repeat so that for those of you who have had the session with P. Thanyapon, you have to thank her for that. That is not what she has to do, but she did it. So, and I didn't tell her to do it too. She just did it on her own instinct. So let us see that this is the purlin, right? So generally, this is the tributary area that the purlin will be responsible for. So that will become what you now know as the tributary width. Correct? So when you look at this purlin, at this particular purlin, okay, let me, I think the good note just crashed, so everything I open is gone. Okay, I need to use this one. So when we look at that, okay, so let us come back to this again. Now we are looking at this. Geez. What is this now? Excuse me, I think it's, now I lose all the pen and stuff. Okay, I just must fit that one. Okay. So now we are looking at this purlin, okay? The tributary area is this, the yellow area. And so the tributary width is the width between the two adjacent purlins. Or in other words, you could say that it's the spacing, okay? So now if I'm going to draw the purlin again, you see that this is your purlin, correct? This is your purlin. And that's going to be your truss right there, right? Now let's focus on one purlin. That is the truss. Let's say call it T1. It's a name. And your purlin will have the tributary width like that. So it's pretty much the same picture, right? This is the tributary width. Okay, so when looking at the purlin, you can view your purlin as a simple beam, okay, with this load acting on it. And so this load W will be equal to your roof load, okay? Date load, that is the tile that you have chosen, plus the live load according to the load. So this is your roof load. Multiply by the tributary width, let's call this B, right? So you have the load per area on the yellow one, you multiply by the width, it becomes a uniform load, correct? Now, we can say that this is L, so that becomes L. And now you know that your reaction is going to be WL over 2, correct? Maybe I should put them to the side so that they are quite the same. Oh, Jesus. Hate that. It's not good. Okay, so let's do this instead. Okay, So that's a reaction from one side of the Purlin. Now there's a very interesting thing because some students at SIIT did this, which is not wrong, but it's not very popular because if you someday you go and work with a big company that produce a Purlin, they would suggest that you can design the Purlin here. You can see the Purlin, one Purlin, right? But then two Purlin, three Purlins. You can design your Purlin as a continuous beam. So the Purlin here, let's say, interestingly, Purlins can be designed, as continuous beam, meaning that you're going to have Purlin like this, right? They become continuous. Now, can anybody tell me why you want to do something like that? Let us discuss so that you can grasp engineering reasons. Instead of you doing a simple beam, why would you want to do a continuous beam? Now you are in the structural analysis #2 class. You are about to have the homework. You may not get to see that picture yet, but you can guess now.
To review the deflection.
Pardon me?
You would like Nakarin first, right?
Okay, Nakarin, go ahead.
I just get its symmetry, so it can easier to calculate.
Because of symmetry. Thank you for your answer, but not quite. Akrapan, you want to try?
I would like to say that it will reduce the diffraction or the deflected shape of the structure, right?
That's not wrong. That is correct, but it's like your answer is absolutely correct, but you missed one. But you should reach another reason before that deflection. Anyone like to try? Well, just the good old folks, right? Say the ones who always say, they will say the ones who remain quiet will remain quiet. You know, someday when you go out there in the real world, you work, you have to communicate with people. You can't remain silent for the rest of your life like that. This is due to the educational system where when you speak and they say you're wrong, but nothing wrong in my class. Because most of the time we don't do this, you know, we do this. We do a simple beam system. Now, let me say this. When you have a continuous beam, first of all, your moment will be reduced. Okay. When you have more than two spans, this moment is less than WL²/8. That is the direct impact. It's going to come down to around WL²/11, 12 to 15. Okay, so we are talking about the significant reduction of the moment. And when the moment is reduced, of course, so are the deflections. Your structure naturally becomes stronger, so you have less deflection. So it's good that you think about deflection, you know, Akrapan, but somehow you miss the moment, right? So the most important thing is the moment, but be aware that, you know, this is WL/2, right? The reaction here, let's use different color. The reaction here will be greater than WL. Because let's say the load here, if you use a simple beam, the reaction should become WL, right? But because of the continuous effect, which you learn from the homework in your structural analysis, #1, don't forget that it's going to be due this Thursday. You will realize that your reaction of the continuous beam for the internal spans will be greater than the simple beam. But the most important thing is that because this is the bending dominant structure, you're going to have less moment. So the huge company like Bluescope, they do a lot of the cold form structure, which we use for purlins. They would encourage the engineers to design something like this. So that means we're gonna have, you know, some more load acting on the truss. That's one thing. And the second thing is that during construction, you must make sure that your purlin will be, you know, constructed so that it is behaving like a continuous beam. Because if you're not careful and they chop the purlins to the length equal to the spacing of your truss, that it will behave like a simple beam. And you know now the simple beam, the moment is WL²/8, to say the least. Okay, right, so that's one thing. So you're free to do this, but most of the time for construction-wise, people do this. Okay, it doesn't hurt to do this. So now you know, because we have more than one purlin coming in, so we're going to have another one here, we're going to have another one there. So that means the reaction that you will put on the truss here, P, will simply be equal to WL. Correct? Because you have two reactions. So that means, let's say this is my truss configuration, whatever it is. And we want to have that because my support is here. Okay, so that becomes my reaction P. So anybody still struggle to understand this? Huh? P comes from that. Okay, P comes from this. Now, once you can summarize the load on your purlins and you calculate the reactions, they become the load that will be applied on your truss. Anybody still struggle with this?
I have a question at the area of the purlin needs to carry. It should be the area that have the slope,
Generally, no. You know, it is a very good question, and I believe that many students struggle with this. This is not your fault, and I think you struggle because you are looking at the problem in good detail. You look for precision of the analysis. So I would say to answer this very quickly, when you look at the plan, generally you can use projection area, which is the dimension. These dimensions are projected dimension, correct? It's not this one. So let's say you have the truss like this, but then this distance is say 6 + 3, 9 meters. They are the dimensions of the projected area. So this, if I flatten the roof, this becomes my projected area, correct? That's the roof. That becomes the projected area, which is generally the idea that the area that we use to calculate the load, because dead load and live load, they come in like this, you know. It's caused by gravity, so it's like that. So you do not need to worry about it very much. So some students would just go on and try to calculate the times load for this area, right? Oh, bless them, you know. That is very admirable, I have to say. But sometimes it could give you more accurate results as well. But generally, I wouldn't worry about it that much because the dead load and live load, they should come in this vertical direction, correct? Now, let me give you another reason why we don't design the purlin just yet. It's true that the load comes in this direction. So you guys are clear with this one before I go on to this? the additional thing.
For the middle one should be 2P, right? Because we need
No,
to
it's 1P because you need 2 purlins, but each purlin will carry half, right?
Yes. Oh, okay. Okay.
So yeah, let's say I was gonna say that too, but it's just like, you know, so many things to say at once. So see here, details need 2 purlins, but they're just like the purlin on the edge, but each carry half the load of the normal purlins, right? So you can say, yeah, 2P over 2, okay? Because that's what you're gonna have here, maybe, if you are very thorough, okay? That's P over 2. So that's like 2P over 2. If you really want to be correct and if you really want to track what you're doing. So that is a detail that you will use in the construction. But when you do the analysis, that this will do, okay? The additional thing, you know, continuing from what Nakarin has asked is this. Purlin is in this direction, right? And you put something on it, the roof tiles, whatever. So what is true is this. All the dead load and live load, they actually are applied in this direction, right? Which means in the actual design of the purlin, you have to, you know, put the load into directions like these. That's if you go and read some textbooks, that's how they talk about how to design a purlin. And I see it can be quite some daunting aspect of design. And more importantly, have you guys ever heard of the shear center? You have centroid, right? And then you have what we can call shear center. Have you ever heard of it?
No.
So that's good then. A shear center, by definition, is the point on your section where if the load acts on it, your section will not have torsion. So that is in turn the definition of torsion. So let's say if I have a square or rectangle, generally the shear center is where the centroid is. So when you apply the load on this rectangular section, if you apply it like that, you don't have torsion. But if somehow, if your load is off this shear center, your section will twist. Okay? Now the problem with the C shape that people use for the roof is that the shear center, do you know where it is? It's right here. So, you know, no matter what you do, it's going to twist as well. Now, this is the bad example of loading, because if the shear center is there, you know, and you put the load is going to come through the body of the purlin here. It's going to increase the shear center. So the best way is to lay it like this, with the shear center here, and then your load is coming in here. And that is why they need to have a sack rod and everything. Okay. So this is the quite correct design, and they treat the load correctly because the day load live, they actually come in the vertical direction. So I really wouldn't worry about the area of the roof and stuff. But if you want to be thorough and calculate, you know, the true load of the roof, that's fine. I'm not going to say you are wrong, because you look into details. Okay. And another thing is this, I don't know, because we have a TA, so I don't know if some of you guys do this, but this is from the experience that I look at the work of students on SIIT. Generally, you would calculate the area of the roof, right? And then you would count how many tiles you're going to have to use, and then calculate the entire roof load, and then turn it into the load per area. Generally, I was really expecting you to do, because they would give information that how many tiles per square meter you are going to use. For example, they would say 2.2, 2.4 tiles maybe. And they would give you the weight per tile, right? That's information. So I would, let's say if this is 7, I would go on in 2.4 plus 7. That would give me the, oops, sorry. That would give me the date load per area, right? Do you believe in mathematics? This is 2.4 tiles per 1 square meter, right? And now I know how many, how much 1 tile weighs. So I just multiply this with that. I get the date load. Simple as that. And if you have done it the other way around, you count all the tiles and calculate all the load of the date load of the entire roof. You do this, you go back and you see you don't miss much, like 1 kilogram per square meter and so on, you know. So it doesn't hurt much. And this is it's part of you growing up. We can say it's growing pain. And one day you will realize that all we do here is approximation. So we approximate the load, okay, to our best ability. And as long as, say, it's not off by 50%, you know, it can be off by 5% or something like that, we should be happy about it. Because you don't know things for sure. So most of you, if not all of you, will have to start to learn to live with the approximation. Because, you know, some of you will become crazy with the numbers, especially in the next topic in structural analysis. And you would start to write like 10 decimals for a moment. And in the end, nobody cares. Now you can say your date load is 15.625357211068, whatever. Who cares with this? You know, if you're not confident, you can say, okay, I'm going to use date load 20, then that's it. You're safe, right? We approximate things so that the structure that we design to support the roof will be safe. And you must learn when the approximation is okay. And then, you know, when you start doing this, and then your moment doesn't come down to 0 and your bending moment diagram, you go crazy again. Right? The approximation of the load and design is okay. But let's say if you want to do the analysis and you want to come down to the proper precision, you must know what kind of significant figures, what kind of approximation you need. Be a good judge of that yourself. So this will become the load. And now, you know, after you get all the date load and live load, you multiply by the tributary width. Now you have the uniform load acting on the purlin. You calculate the reaction of the purlin, it will become the load acting on your truss. Okay? So is there any question about the load before I go into the truss? Hello? Anyone? So I hope that that's okay for everyone, right? Now, let's take a look at our plan again. Now, some of you will be concerned that actually you have one main truss here and then another here. Okay, So this is not a very huge project. Let's say in the huge project, you will save some money by designing another truss here for the ones on the edge, because it carries say half the load. But because you have this, you know, overhanging area as well, so in the end the load isn't much different. So it is okay to just design one truss number to use for the entire roof. Okay, you guys got that? And another good thing, I think Sipka, right? You asked me that. You asked if you really need to have the beam here. Okay. Generally, let's say if this is your roof plan and you design only the truss and you don't have this screen beam, your entire structure will not be so stable. Even though theoretically, yeah, everything is okay. But in the real world, you would want to have some beams to tie your columns over in this direction as well. Okay. And I'm pretty sure that Ajahn Sutat will want you to have this when you design the frame. So, okay. We may not design this just yet, but keep in mind that in the real world, you would want to have this to provide proper stability to your entire system. All right. Say now, let us go back to the truss. Okay. Just one truss. Oh, wrong one. So let's keep to this. Now, let me repeat again. See, that's bad English. When you say repeat, you don't say again because it's repetitive. So I want to repeat this. Okay. This is the picture of the truss that is drawn in the architectural drawing. So we don't pay attention to this. What the real truss look like will depend solely on you guys. You will have the final say of what the truss would be, not the architectural drawings. Okay, you don't design the truss because you know the architectural drawings have this kind of configuration, so you use this. That reason will not win any argument. All right, it's your job. Even though this picture is nice enough. Okay, so is there any question about this? So we move on to the truss. Let's say I have to draw that truss again. I deliberately draw the truss that will not look the same as the ones that you use. Okay. Now you know you have this extension. So I say, ignore that. Okay. Ignore that. So now you know you are going to have the support that perhaps it's like that. Okay. Now I would want to have maybe this. Now the problem with this truss is that it will look just like a cantilever beam. An overhanging beam. Okay. So let's say I put the load on it. You know that this is here is a positive moment. But here is the negative moment. So what does it mean? It means that around here, listen very carefully, okay? Around here, your top chord may be under compression. This one could be under compression, maybe. Oh, but here is the support, so chances are, no, it's not going to be under compression. I don't think so. Anyway, okay. This is probably be under tension. Okay, now in turn, what is worse is this. If the top chord on this region that you see here is under tension, that means, you know, it's a beam, right? So this two member may be under compression. Okay. Wow. And that will be under tension. So I'd say many times if you have noticed truss members, they would tend to use the same members for top and bottom chord. Okay, it's kind of rare to use the different members for top and bottom chord. It's easier for construction as well. So now I would suggest that the members that you should use is going to be either square or circular. Okay. Now these two, you know, square, you have a doubly symmetric section, but if it's square, your Rx and Ry be equal anyway. So you just check one R, and the circle, there's no need to talk about it because it's just one R anyway. Okay. Now, the issue with this is this. The compression member, if you look at the top chord, you see you're going to have purlins here, right? So the purlins will help brace the out of plane buckling of your top chord, correct? And the in plane will be braced by this joint. So it's safe to say that this member, the unbraced length in both axes are the same. Are you following me? And that it becomes the unbraced length, which is equal to the L, the length of the member. Or, well, to be clear, it's this length. Right? And out of plane, you are allowed to use K less than 1. So that means the in-plane bending, K equal to 1, will become your governing case. So you may as well design this with just K equal to 1 and then L as the length of this member. So it becomes quite simple. But, you know, it's simple because I have done the assumption for you. Keep that in mind. When you go out in the real world, it's you who have to make this assumption. So for those of you who just, okay, now I know this is my KL, so I don't care about anything else. I just know that the length of the member becomes my L, so I have to focus on my design. Yes, you're going to be okay for this particular project, but you may not be able to, say, extend your ability beyond what you have here if you don't understand this. Okay. Now this becomes more troublesome because you don't have anything to help brace here. Okay. So that compression member, wow, I honestly cannot give you the, say, the clear definition of what you should do to handle this one. Even though you have the purlin here at the end, and you may argue that this will help brace the this compression member, but I wouldn't say it's gonna be, 100% held that. But yes, you do have a Purlin to help out, unlike this one where you don't have it. Okay, so what we can do here is, let's say I'm going to draw the side view. Okay, so now we can look at the truss from this view. So now your truss becomes something that looks like this. And then you will see your purlins coming in. Let's say put some dimension on, okay? Say maybe like that. Then your purlin is like here. Okay, you have two purlins. So now you can see that if this is a compression member, it's all alone. Okay, but let's say because this is entire member and they say, but you don't have the brace point here. If you want to design something, even though this is under tension, I would not design this as the length of this member, even though you may use K equal to 0.7. Okay, so what do we do? You can do this in the real world. You can say, I'm going to use a different color. What would it be? You can add a kicker from the purlin. If that's the case, it will help brace this bottom chord, and you may extend it here. And sometimes instead of doing this, you may see that the many systems will have the sub truss coming in to help brace this point. That's the purpose of the sub truss. Okay, so you can do this, or you can have the sub truss system, so that this unbraced length becomes just this length. Now, on paper, you may design, let's say, hey, I'm going to design this as my unbraced length. But say if you fail to provide information like this, your structure would not behave the way you want it to behave. You want it to behave. Okay. Any question? I think we should have a break. And then we'll come back and wrap up the entire thing next hour. It's getting too long and you're going to be too tired. But next hour, it should not be like 1 hour because we are nearly the finish line. Okay. Any question?
Excuse me.
Yeah.
From my the selected tile for my project, the spacing for the purlin recommended is about this 30 centimeter. But
okay. I thought nobody had that in this class. So thank you for asking, Napat. For those of you who have chosen the tile with the small spacing system, I believe that they are going to have some kind of a substructure to support that before putting them on the purlin. Okay, because it is very impractical to have the panel of the truss like every 30 centimeters or something like that. it's just some kind of a CPAC monia, right? They have a subsystem like that looks like a mesh with the small steel and stuff. They put the tiles on this mesh system, and this mesh will again be supported by the purlins. So for those of you who have chosen the tiles with the small number of spacing like that, please, you can use the purlin every 90 centimeter or 1 meter or so. Okay.
Okay, thank you. So should I include the additional structure?
No, because if you choose that kind of ties, I think they are already heavy enough.
Okay, thank you.
Good. So, is there any more question? Let us